here we're going to talk about stability of the replicator dynamics equations. So the replicator dynamics equations are dxi dt equals xi times fi minus phi for all I. And so the replicator dynamics equations indicate that a population is stable, in other words, does not change over time, when dxi over dt equals 0 for all I. Now, this means two things. This means either there are no more individuals of type I in the population, so xi equals 0, or the fitness of individual I is equal exactly to the average fitness, okay? As an example of this, we'll take a look at rock, paper, scissors. And in a previous video, we wrote down that the replicator dynamics for rock, paper, scissors were dx1 dt equal x1 times x3 minus x2, dx2 dt equal x2 times x1 minus x3, and dx3 dt equal x3 times x2 minus x1. That's not self-evident. That's the replicator dynamics equations for rock, paper, scissors. We did in that previous video, and a little bit of work we arrived at these equations for rock, paper, scissors. Now, for all of these to be 0, which is the requirement for our population to be stable, for all of these to be 0, we have a couple of things that must happen. So move this over slightly. For all of these to be 0, we have that x1 must equal to 0, or x2 must be equal to x3. We have that x2 must be equal to 0, or x1 must be equal to x3, or x3 and x3 must be equal to 0, or x1 must be equal to x2. So we need those three things to happen. And if you inspect that a little bit longer, keeping in mind that we have to have some population, that not all the x's can be 0, this in fact leads us to this set of conditions, that we have x1 different to 0 and x2 equal x3 equals 0, or, and here this is very much an or, oops, sorry, I'm not on the screen anymore, or x2 different to 0 and x1 equals x3 equals 0, or x3 different to 0 and x1 equals x2 equals 0, or the final possibility is that x1 is equal to x2 is equal to x3. And these three populations, these three possibilities lead immediately to the following population vectors that are stable, which is 1, 0, 0, so nothing but individuals of the first type, so nothing but rocks, nothing but papers, nothing but scissors, or indeed exactly a third of each. And so these four populations are all stable. If you plug them into the replicator dynamics equations, the derivative would be 0. And what we can do is we can solve the replicator dynamics equations numerically, and this is what we obtain. And here, this is starting with the entire population of rocks, and we see nothing changes over time. This is starting with the entire population of x3, so scissors. This is the entire population of paper, and here is starting with everyone at a third, which is the only way we can get everyone equal when they sum to 1. And you see all those populations are not changing over time, so they are indeed stable.